Hi, understanding the decision-making process of image classifiers is a critical concern in the field of machine learning. When the classifier acts as a black box, we can formulate its explanation as an optimization problem over a deletion mask. In essence, the smallest region of the input image that preserves the classifier's prediction is presented as the explanation. Past research has indicated that without regularization, explanation masks lead to sparse high-frequency patterns that can trigger the class label but fail to explain the classification process. Meanwhile, smooth masks fail to highlight relevant fine details, creating a trade-off between artifacts and detail clarity. Our work is fundamentally guided by a theorem we've developed stating that no new edges are introduced when applying masks in shearlet or wavelet space. Building on this theorem, we present ShearletX, a novel method that masks and shearlet representation to prevent oversmoothing and artifacts. We also introduce new metrics to quantify artifacts. Our first concern was identifying a method to quantify artifacts in mask explanations. We noticed that artificial edges, those present post-masking but not pre-masking, often generated artifacts. Take the barn image with a sparse pixel mask explanation. Numerous artificial edges, highlighted in red, can be seen. These edges can create hallucinations, which are misleading patterns activating the class label without providing an accurate explanation of what's going on. We quantify artifacts using the hallucination score, computed as the ratio of edges exclusive to the explanation image to the total number of pre-masking edges. A high hallucination score, such as for the sparse pixel mask, indicates artifacts. Note that the smooth pixel mask has a very low hallucination score and does not produce artifacts. Before discussing our theorem, let's review the definitions of wavelet and shearlet transforms. The wavelet transform of an image, denoted by f and modeled as an L2 function, is the inner product of the image and a dilated, translated, and directed oscillation psi, the mother wavelet. For the shearlet transform, we further define the shearing parameter. The shearlet transform of an image f, modeled as an L2 function, is the inner product of the image with a dilated, translated, and sheared oscillation phi, the mother shearlet. The key difference between wavelets and shearlets is that wavelets are isotropic, whereas shearlets are anisotropic due to their shearing parameter. This is why the shearlet representation provides such a highly efficient representation for images with anisotropic features, such as curves and edges, and is more efficient than wavelets for such images. Now we can state our theorem. Let X be an L2 image and M a bounded mask, either in wavelet or shearlet space, and denote by X hat the image X masked with M in shearlet or wavelet space. Then edges in X hat are a subset of edges in X. In other words, masking in wavelet or shearlet space did not create new edges. And our theorem relies on Lipschitz continuity in the wavefront set to model edges in L2 images. To prove something about edges of continuous images, you need to have first a mathematical model of what an edge is. But we refer to the details to the paper. And as we will see later, we can also confirm that empirically that our theorem also holds approximately for discrete images, which is what we use in the real world. We don't model images as L2 functions, we have discrete images. Our theorem motivates the shift to masking in wavelet or shearlet space rather than pixel space to circumvent the creation of new edges, which potentially form artifacts. In previous pixel mask methods, we maximized the expected probability post-masking and perturbing in pixel space while maintaining minimal mask coefficients and regularizing the mask for smoothness. The coefficients of the mask can be minimized with an L1 regularization, of course. Our methods, ShearletX and WaveletX, instead of masking in pixel space, mask in shearlet and wavelet space, respectively. So Z is either the shearlet or the wavelet domain. And they also encourage, of course, for mask sparsity to keep as little information as possible, but we do not regularize for smoothness because we can protect against artifacts by masking in the shearlet or wavelet domain. Instead, we penalize unnecessary spatial energy in the pixel domain because low frequency patterns can occupy a lot of spatial energy in the image, while being sparsely represented in the wavelet or shearlet domain, meaning only having the L1 penalty on the mask isn't sufficient and we need the spatial energy penalty. The optimization objective is then solved with SGD over the mask with a simple sample average estimate of the expectation. To definitively demonstrate that ShearletX provides more detailed explanations than smooth pixel mask, we require a metric that measures the precision and conciseness of a mask explanation. We will represent the coefficients of an image in a certain representation, pixel or wavelet or shearlet representation, as Ci. We then define the retained image information as the ratio of the information in the image post-masking to pre-masking. If we use entropy as a measure of information, which is commonly done in information theory, we can compute the image information with the exponential of the entropy produced by the distribution that is induced by the image coefficients. Alternatively, we can also, of course, use sparsity instead of entropy to measure information, and we experiment with both. In any case, we can establish then the conciseness-preciseness score, short CP score, as the ratio of the retained class probability to the retained image information. The retained class probability simply refers to the ratio of the class probability post-masking to the class probability pre-masking. So the retained class probability should be high because we want the explanation to be precise. We still want the prediction to be retained. And a higher CP score indicates a better mask explanation. In a large-scale experiment involving 1,000 explanations for pre-trained ImageNet classifiers, we can confirm empirically that ShearletX avoids artifacts while producing more concise and detailed explanations than smooth masks. Each scatter plot shows the hallucination score to measure artifacts on the y-axis and the CP score on the x-axis. The first scatter plot uses entropy-based CP scores, the second uses sparsity-based CP scores, and the final plot uses sparsity-based CP scores, which have been exclusively computed in the pixel representation. As predicted, sparse pixel masks lacking smoothness regularization display an unacceptable level of artifacts, rendering them unreliable for explanation purposes. In all three plots, ShearletX notably outperforms other methods, achieving the highest CP scores and thus providing the most concise and precise explanations. Both WaveletX and ShearletX demonstrate substantial protection against artifacts, validating our theorem by having very low hallucination scores. While WaveletX and ShearletX exhibit higher hallucination scores than smooth masks, our empirical verification confirmed that these scores do not result in significant artificial edges or artifacts. Thank you for your attention, and I hope to see you at the poster.